Hi, everyone. So today we're going to go over a couple of different exam FM SOA questions that are from the Society of Actuaries. We'll go over, I've already solved a lot of these, and I'll go over the steps behind how to solve them. And is this frozen? Okay, there we go. The steps, how to solve them, and some of the tips and tricks when solving these problems. Because it's important for when you're preparing for this exam, not to just solve the problem, not to just look at the solution, understand how to do the problem, but also some of the tricks and patterns of patterns of the types of styles of thinking that you want to have when you're doing these types of problems. So we'll go over a lot of that here today. So let's start with question 254, and this is from SOA exam FM sample questions. You can get this just by Googling SOA exam FM sample questions. Like the first thing, the second link has like the 2018 sample questions. So just click on that and you can get this. I think it has like 400 types of 400 questions. So 254, perpetuity immediate is purchased at a price of 5,000 based on an annual effective rate of I, where I is greater than zero. The perpetuity pays 150 in the first year, increases by 10 each year thereafter. Calculate I. But immediately from the fact that we know it's a perpetuity immediate, we know that this has a constant payment amounts every single year until infinity. There's no end date. Purchase price at 500, so that's why we know that present value at time zero is 5,000 or 5,000. And then just the first thing you want to do is draw this time diagram. This is similar to what you want to do in every single problem when you have a perpetuity or annuity due or an annuity immediate, or where you have these payment patterns. Draw a time diagram where you can visualize when the payments are actually being made. So that's the first step here, is to do that. So at time one, we have 150, and then at each time step, we increase by 10. So at time n, we have 150 plus n minus 1 times 10, the payment. That would be the payment. And so we already know that the present value, the formula for this is the first payment over I plus the difference, common difference over I squared. So we can just plug that in here, 150 over I plus 10 over I squared equals 5,000. Just solve for I. So this is a pretty simple problem, but one of the things that you can learn from this is A, drawing the time diagram, seeing where the payments are actually being paid, and you can intuitively, immediately recognize the formula that, hey, this is a perpetuity. This is a arithmetic progression problem for infinity, and you can just remember that formula. And another thing is you want to really learn it deeply with fewer questions. So it's more important that for not, yeah, you want to do as many practice questions as you can, but really for each question, for each difficult question, you really want to think about what was my thought process? What are some patterns I can get into that can help me more easily solve these types of questions? So for example, in this case, it was drawing out the entire time diagram or immediately recognizing that formula, really having it memorized. So you really want to, with fewer questions, you will really want to understand the patterns of those questions so you can apply that to future questions. And so another thing is if you do not know like a question how to answer it in 3 minutes, then it's important for you to move on. Right? This is a very time intensive exam. You only have like around like 4 minutes per question. So if after a first read, if you think that you're not going to be able to solve this in like 5 minutes, that's very important for you to just keep on moving instead of spending like 20 minutes trying to solve the question. You may not even get it right. So you want to really be aware of the time that you're spending on these types of questions. So that was 254. 238 is also about annuities, and it's pretty similar concept. So a perpetuity makes payments every 5 years with the first payment of two to be paid 5 years from now. So we have the first payment of two 5 years from now in our time diagram. Each subsequent payment is 10 more than the previous payment. So we add 10 for each payment afterwards, and the annual interest rate is 9%. The first thing that or one of the key to notice is attention to detail of the keywords. So here we see that the annual effective interest rate is 10%, but here we see that we're talking about, in this case, like each payment is every 5 years, right? So our time interval should actually be every 5 years. So we need a way to convert this annual effective interest rate to like a 5-year effective interest rate. So we're able to do that just by here. And once we have this new interest rate, then we can simply use the perpetuity or the formula for arithmetic progression for infinity, and we can substitute that here to get our 38.18 present value. So the key concept to learn here is you really want to have attention to detail of keywords, right? If you're just using the effective annual interest rate of 9%, you're probably going to get a different answer. You have to go and redo the problem, reread the problem. So it's going to take a lot of time. So you really want to pay attention to these details here. Like it says 5 years, the payments are every 5 years. You want to have a 5-year interest rate. And then 299, an insurance company has a liability of 2662, so it's has to pay out 2,662. It's due at the end of 3 years. The present value for this is 2,000. So now you can solve for the interest rate just by doing 2001 plus I to the 30 equals 2,662. You get that to be around 10%. There are two investments available: a zero coupon bond and a 4-year coupon bond. We want to find what's the investment plan that satisfies Redington immunization. So as soon as you see Redington immunization, like two things should immediately flag. That's the present value of the liability equals the present value of the assets equals the present value of the assets. And then the second one is that the Macaulay duration of the liability should equal the Macaulay duration of the assets. So here you can get two different systems of equations that you can solve. And there's a third regarding convexity, but in this case, we only need two. And typically, you will only need to really solve these two systems of equations to get the values. So in this case, again, first thing, draw our time diagram. This is like a thing I keep on reiterating, but this is really essential. Drawing a time diagram, you're able to visualize where the payments and the assets and the liability are, and it just helps you visualize the problem in a much more clean manner. So we draw our time diagram. We know the present value is at 2,000. At time 3, it's 2,662. And we know that's a 1-year coupon bond. So our redemption value is going to be X for that. And then our redemption value for Y for at the end of year 4 for that 4-year coupon bond is going to be Y. So first we set so these are the two system equations, setting our present values equal to each other, setting our Macaulay durations equal to each other. And then we just solve for X and Y. And we're able to get our answer of around 667. That's the value for X. This is the value for XV because we have to get the present value, right? So we're calculating XV in this case. And then for 32, a common stock. This is actually a very important problem because it helps you really understand. Because initially, when I was going through this, it took me a lot of time to actually figure out the pattern and how to solve this question. But if you just lay out the formula and you really think creatively about like interest rates and how they work and how you can change them just slightly to find the answer to this problem, it's important and it's going to really help you. So it pays dividends at the end of each year into perpetuity, assuming that the dividend increases by 2% every year. So here we see that we have payment. So it doesn't give you the actual payment. So here you probably, because it doesn't give you the actual payment, you can there's probably some sort of cancellation process where you can eliminate the payments themselves. So that's an important thing. If they don't give you like a certain piece of information, that's probably like, okay, you can probably ignore this, or when you're solving it, it probably cancels out somewhere, and which is exactly the same case, which is the case here. So first we draw our time diagram as we've done in previous questions. We have X representing the payment amount. It increases by 2% each year, the payment, and we want to calculate the Macaulay duration. So as we know, the Macaulay duration, the formula for that, we take the time times the discounted cash at that time, and then divide by that present value, and then the sum of all of that. So here we can see the present value is calculated the denominator, right? That's just XV plus XV squared times 1.02 plus XV to the this should be there should be 3, right? 3 XV3. Yeah. And once we have this, we can see that we can cancel out all the x's. So we're left now with b plus 2b squared times 1.02 plus 3b cubed plus times 1.02. And then in the denominator, we have the same thing, the present value. Now, one of the adjustments that we can make here is in terms of the interest rate. So the interest rate in this case is just 5%. We can actually change this depending on how the amount that we're increasing our payments by. So in this case, we're increasing the dividend by 2% each year. We can actually adjust our interest rate to account for that increase. So we have this new interest rate that takes into account the old interest rate plus this additional increase in payment each year that you get. So this is the key in actually solving the question. So in this example here, you can see that when we're summing each individual discounted cash flow, right, we're seeing that we're multiplying by V and we're also multiplying, so in this case, like the common ratio is v times 1.02, right? If the common ratio was just v, then it will simply be, I would be our normal regular interest rate. But because our common ratio is v times 0.2, we can actually use this because we know that if it's just v, then it's our old interest rate, right? But now we know that if we have this as our new common ratio, we can set that equal in the same way that v equals 1 plus I, because this is our new common ratio now, right? We can set that equal to 1 over 1 plus j, where j is our new interest rate that takes into account the amount that we're increasing by, the 2% that we're increasing by. So once we figure out our new j, you can think of this as like a new interest rate that takes into account the increasing the 2% each time period that we're having these dividends. And so now that changes how we can solve the problem. That makes the problem a lot easier, right? If you're just trying to solve this, it becomes difficult. If you're just trying to solve this equation, it actually becomes very difficult because we don't have any form, because this itself, if you look at the we can solve the denominator, but if you look at the numerator, it's the 1, 2, 3, that's an arithmetic progression. The v squared, v cubed, that's itself is a geometric progression. So how are you supposed to like sum arithmetic and geometric progressions like all at the same time? But we can do that by having this new interest rate. So when we have this new interest rate, this essentially, this v squared times 1.02, this v cubed times 1.02 squared. Now essentially they become our like new v, right? They become our new v that we're discounting by. And so now in the numerator, we just have an arithmetic progression to infinity. In fact, it's a unit arithmetic progression to infinity because it's simply just our new v, let's call it vj, plus our 2 vj plus our 3 vj, or plus 2 vj squared plus 3 vj cubed plus 4 vj to the fourth, on and on, which is a unit progression, which is a unit arithmetic progression to infinity. So you can use our formula here. And then in the denominator, that's just a simple perpetuity, right? That's a simple perpetuity of just 1. Because we've already said that this is this is our new v, right? So we're just adding up a bunch of ones here. So that's 1 over, we're adding up a bunch of ones to infinity. So this is just 1 over our new interest rate. So now we have this new formula, 1 over j plus 1 over j squared, divided by the formula for a perpetuity of payments being 1. And so now we have our formula here. We're able to substitute. We find that j equals 0.03 when we figure this out. And then we're able to substitute into this formula, and we get around 35 being the answer. So one of the key in this problem is that if you just look at this problem and if you just look at the formula here, it's going to be very hard for you to come up, and you're just acquainted to using the formulas that you've learned, and you're not really being creative with the concepts and thinking how can you change the interest rate so that you can solve this question. If you're just thinking about what you've already learned before and just trying to use that, then this problem becomes pretty difficult to solve, because especially in the numerator, we have arithmetic progression and a geometric progression to take the summation of. So that's going to be pretty difficult. But because you can be creative with these ideas of interest rate. Let's try to find a new interest rate for this, right? This is not something like typical that you can just it's not like a medium level of thinking. Like you really have to be creative with the ideas here that you're learning. And so once you have the new interest rate, then you're able to solve this question. So you really want to be creative with the concept. That's one of the things we learn here as well. And I would say this is probably like one of the more harder questions. But I just wanted to include this just for the teaching, that you want to be creative with the concepts, not just think about what does this question fit into what I already know, but how can I use what I already know to make changes to what I've already learned, to like play around with the interest rate, play around with these concepts to make it fit the question so I can solve the question, right? So that's one of the things we learn here. In 75, question 75, a couple decides to save money for their child's first year college tuition. The parents would deposit 1,700 end month from now, and another 3,400 to end months from today. All deposits earn interest at a nominal annual rate of 7.2% compounded monthly. Calculate the maximum integral value of the end such that the parents will have accumulated at least 6,500 5 years from today. So first thing is, because it's compounded monthly, we want the month interest rate. We divide that by 12. That's our monthly interest rate. Now we go from 0 to 60 months because we're 5 years at 60 months. We're in terms of months here. Then we just label our payments, right? So we at time n, 1,700, time 2n, 3,400. Now let's bring it all to present value. We're saying that the parents will have to accumulate at least 6,500 from now. That means accumulating at time 0, whatever the present value of that 6,500 is at time 0, when after we've discounted the payment at n and the payment at 2n at time 0 as well. So that's what we do here. Discount those two payments at time 0, discount the 6,500 that we have to accumulate at time 0, and then solve for n. In this case, we're not actually solving for n. Okay, and this is one of the things I want to get into. So after we solve for n, or after we set up this equation, we know what n is, or actually we don't know what n is. We know what v is. We're solving for n, but we're not actually solving for n. So I'll get into that. So this is the final equation. Now, if you wanted to solve for n, you could like do the log. You could take the natural log of both sides and use your properties, and you can eventually find some solution, or a quadratic formula. You can find some solution for n. But in the case of time, or in the case where that's might not be apparent to you, what you can do is, because we only have 5 answer choices here, you can plug each of those in and see which of these would give you the value. And this is one of the things, one of the strategies you want to keep in mind is, this is a multiple choice test. Whenever you get to a question where it's like, let's say a quadratic that you have to solve, or it's a messy equation that you have to solve, and you don't really want to go through the steps of solving it, you could just plug and chug and see if your answer makes sense, and just see if you can get an answer. In this case, when n equals 11, our present value is greater than, I think it was 4560, which is greater than 4539 that we need here. So this, and then when we tested out 12, it gave us an amount that was greater than 4539. So we can see that just by plugging and chugging, we can get the answer, and probably much quickly than if we were to like do the math and set up the equation, quadratic formula, or natural log. And there's probably more errors to that as well. So plugging and chugging actually, A, might save more time, and B, helps us eliminate those errors as well. So that's one of the strategies. We have 5 answer choices. It's a multiple choice exam. Let's use that to our advantage. And whenever we see a question where we have this quadratic equation or some sort of equation we have to solve, let's instead, if it's easy, to go ahead and do it. And if it's something simple, but if we think it's going to take a lot of time, let's use the fact that we only have 5 answer choices to our advantage and plug these in to see what answer that we are able to get. So I just want to go through a couple of these strategies. Now let's go through NFL Week 3 predictions. So we've already predicted the Jets to win. That was pretty easy prediction there. Obviously, the trend for that was consecutive Thursday night upsets do not happen. So we saw that also at Rodgers MVP prediction still remains strong. I think the PFF, he's the third highest rated quarterback. Pass rating above 100. I think yards per attempt is also good. I think 4 big time throws, which are like 20 plus throws down the field, 0 turnover worthy plays. Even the pick in week 1 wasn't considered a turnover worthy play because it was a tip. And then this week, the thing that the team I'm most confident is Ravens money line -110. Again, good value here because it's -110. They're only favored by like I think -1.5. So it's a good value here. And the trend for this is that Cowboys upset the Browns week 1, 325, and it's very rare to have for a team to have consecutive 325 upsets when the game starts at 325. So that's a trend here. Lamar versus NFC teams, I think he's like 10-1 maybe, or even a perfect. I think he's only lost like one NFC team in his career, or it could have been perfect. Basically, the point is he's extremely dominant against NFC teams if you look at his numbers, if you look at his record. And then favorites, and this is one thing I'm keeping track of, is like favorites. The Ravens are favorites here, and so far we've had around 43% upset so far. So If that number was actually down to like 20% or 30%, then I would be a bit more hesitant because that suggests that hey, maybe more upsets are to come later on, maybe even in this week. But the fact that we've had around 43 upsets so far, and just so you know, like the general trend is like 40% upset, 60% favorites. But the fact that we have seen a 43% upset, which is like the general norm, that leads me to believe that uh, just brings me more confidence in this pick. And then some of the trends like I realized like over the past 2 weeks that don't necessarily work, and you can see with some of the parlay predictions I made some videos back, is that the largest favorite of the week does not always win, right? We've seen this with the Bengals upset by the Patriots. We've seen this with the Ravens upset by the Raiders. And a team can also do multiple, like even double-digit upsets in a given season. So we saw last year the Cardinals beat the Cowboys. I think they were like 12-point favorite. And then later in the season, Cardinals beat I think it was the Eagles, right? I think they were 13-point favorites. Eagles were 13-point favorites or something like that. So a team can do multiple, is able to do multiple, even double-digit upsets in a single season. So don't bank on the fact of like, oh, if a team did like a 10-point upset in 1 week, that's probably not going to happen. The rest of the season might even happen the next week. So that's one thing that one of the trends that I've learned that don't always work here. And one of the trends that I'm like experimenting with this week is so last year the Packers upset or last week the Packers upset the Colts at 12 o'clock game, and that was actually considered like an upset. So the Colts were favored. So NFC upsets AFC at 12 o'clock games. Following week, no NFC team will upset AFC team at 12 o'clock games. So if in the previous week the NFC team has upset the AFC team at 12 o'clock games, in the next week, in the following week, no NFC team will upset AFC team at 12 o'clock games. This is a trend that I've sort of seen, and I'm really seeing if this actually works. And I'm using this as an experiment this week to see if this trend actually works. Because this week we have a ton of NFC teams that are favored against AFC teams, and I want to see if this trend actually holds. So this would be a good experiment. I think this is like Bears and Colts, Texans, Vikings, Browns, Giants. So this will be a good week to test this trend out as well. So that's about it. And yeah, that's about it. Point of this video mainly to go through. Point of this video is to make sure that when you're doing exam FM questions, you want to understand the patterns of thinking in these types of questions. Don't just answer the problem, just figure out the solution, but really dive deeper into like what are the common things that I should always be doing when I'm performing these questions, and drawing these time diagrams, figuring out plugging in the choices instead of just solving for the variable, right? That may save a ton of time. Being creative with the concept of interest rate, how you can adjust that to solve something that you might think is pretty difficult to actually do, right? The summation example here. So just being mindful of these things, and the more practice that you do, it's obviously going to be better. And then the last one is doing easy questions first. Again, very time intensive exam. If you don't know the question in like 3 minutes, move on to the next question. It's going to save you a lot of time and energy for the later questions. If you spend like 20 minutes and there's a chance that you might not even get that question right. It's a waste of 20 minutes. You're better. Every question is worth the same amount. You're better off moving on to the next question and doing the easier questions first. There's no, oh, you got this more difficult question correct, you get more points. It's not every question is worth the same. So, great. So that's it. I'll see you in the next video. Thanks, guys.